So we continue. We were talking about the registers. We had 3 registers for the timer of this device. The first one was the control register, and with specific bits, we have changed the control and just control the status of the timer. And we have the reload register, which was for setting the maximum value. The maximum value was decremented one by one up to 0. So if the maximum value was n, we had a modulo of the counter, which is the periodic size of the counter in indices, n plus 1. That's why if you're running in 16 megahertz, which we will be creating n plus 1 times this value nanohertz of period for the timer. And the actual value of the timer was kept in the so-called current register. And if the control register was enabled, it was going to decrement from the top value, which was in this register, one by one. Okay, so we have an idea of how it operates, and we can create a scenario of how it's going to operate. And actually, since we have to set some control registers to make it work, it needs an initialization procedure, because as you all know, if you want to make a device work on an embedded system, it could be an external device or an internal pad like GPIO or an internal circuitry like timer, whatever. What you do is you set the necessary control registers once at the beginning, and that procedure is called initialization. We have to make a timer initialization. So let's try to make sense of what the steps of these initializations are, one by one. So guys, when enabled, the timer counts down to 0 at each clock. So while we are initializing, let's not enable it. Let's disable it, because when it's enabled, whatever the value, it's going to count down. I mean, if you want to make a precise timing of something, we want the timer to begin at an exact time. So while initialization, let's not enable it. Let's disable it first while we are setting the necessary values. So after 0, if it is enabled, it's running, it wraps to the value of ST reload. This is important, guys. What it is trying to say is, imagine it was set to 6 and it's counting backwards. While it's counting backwards, because it's happening automatically, we don't do anything. So while it's counting backwards from 6 to 0, I could do anything in the main code. I could do some instructions. And imagine I changed this register, the reload register, to 8, somewhere around here, while it was counting back. The mechanism is, it comes to 0, it just does not jump back to 6 because it was the previous value. At 0, it reads the reload value. If it is changed to 8, well, it starts counting from 8, not 7. So at each hit to 0, it checks the reload value and loads it to the current value. That's the mechanism. That's how it's wired. That's the architecture. So that sentence was explaining that actually. I mean, after 0, timer reloads or wraps to the maximum value, to the value which is actually written at that moment at the ST reload maximum value register, and continues at the next clock edge. Any questions? So reload n value is written to the reload register. We know that. I mean, the maximum value which is going to be set when the timer hits 0 is kept in reload. So reload register is like fixed. It is showing you the next maximum value which will be written to the timer when the timer hits 0. Good. Clearing ST reload register makes it 0, guys. So if you make this ST reload maximum value register 0, the timer becomes 0, and it's a decrementing register. It will be like 0, decrementing it to 0, loading 0 again, 0, 0. So it is like the timer is not working. That's why actually clearing the ST reload register, in other words, making the ST reload register all zeros, is identical to disabling the timer. So you can disable the timer by making this 0, or you can disable the timer alternatively by making the ST reload register 0, because it's going to be always 0. But just let's do it by there's an enable bit here. So ST reload register is meant to be some non-positive value, non-zero value, a positive value. Okay, when the counter reaches the 0, be careful. Two things happen. This one, ST reload value is set to the current value, and the count flag is set. What was the count flag? We talked about this. This is set. This is 1. And if you read that, it becomes 0 again. If you don't read it, it stays 1. Strange behavior, but that's the design. So that's how it works. Be careful, guys. You can debug your code. You can debug this device on Kale. So does the timer stops during debug? Yes, because during debug, the internal clock of this device is also halted. Halt means stop, but it is usually the word used for stopping the clock. So the clock is halted. When the clock is halted, everything is halted. It is like a freeze. It's like a status chamber for this device. It is created another dimension in time and jump there, because in its own world, nothing changes. Every register stays the same because clock is fixed. So in debugging, the timer will stop. That's why we'll be able to check the timer. However, if you want to get the exact amount of time between two button presses, for example, you cannot do it in debugging mode, because in real time, the time will pass, but the clock will stop. So in debugging mode, we'll have some special analysis and blah, blah. You'll see. So be careful. In debugging, the clock stops. That's why the timer also stops. So we have a basic idea of how to make it work. If we knew the addresses of the control registers, we could do it. Let's do it. Okay. Operation of the SysTick timer in M4. We are step by step getting there. The final and most important rule, the STCURRENT is a read-only register. I mean, you load the maximum value to reload register. STCURRENT just decrements. It changes of it on its own. If you try to write something on it, it is write aware. It will be aware of the fact that you are trying to write this. This is the current register. If you try to write it, it won't allow you to write it. But it will take it as a message. Which message? Writing to STCURRENT clears the register. It would think that you are trying to reset the timer. So a way of resetting the timer, because you can set the maximum value of the timer, but you want to reset it at some time because the timer is running and you don't know what value the current register has. You want to reset it. You want to make it 0. What you should do is try to write on the timer. Whatever you try to write, try to write 1, try to write 10, doesn't matter. It's going to be 0. Okay? So you won't be able to write a specific value. You can only write 0 to it by trying to write any value. What is trying to write? Well, we'll get there. And on a read, well, it's okay with that. If you try to read the current value of the timer, you will simply get the current value of the timer. So you read it. You read it in next sometime later, it will be decremented. If it reaches 0, it will be wrapped up to maximum value and it will be another value. So you can read it periodically in a loop, for example. We are going to do it. So if you want to read the timer, if you want to check the clock, if you want to read the watch of this microprocessor, you read this timer by reading this register. Okay? Simple. Now the diagram. I love this diagram because, guys, everything we have talked about is hidden in this diagram in a logic design way. This is how architectures put it. So it is, again, a computer architecture analysis of the microprocessor device. Guys, this is the counter. So this is the current register. Current register. And this is the ST reload register, this one. This is the current register. As you can see, there are nice arrows showing it. Okay. And this is the control register. So this is the first register. This is the second register. This is the third register we have learned. Now there are some logical connections in between. Do you remember what was the least significant bit of the control register? This one. Does anybody remember? It says so here. Enable register. Do you remember how it worked? If it was 0, the timer was frozen. How come? There's a wire connected to this bit. So if this bit is 0, this wire is 0 volts. If this bit is 1, this wire is 3.3 volts because logical 1 in our system is 3.3 volts. It is connected to this AND gate, guys. As you can see, can you follow the red cable connected to enable? And the other pin of the AND gate is connected to a clock. Which clock? I don't care. This is the clock. So clock is coming in, guys. So if this is 0, no clock will be coming to the counter. So it's going to be frozen. That's how you enable and disable the system. So just by looking at this diagram, I can understand that if enable bit 0 is 0, the counter, the timer will be frozen because it's ended with the timer. If it's 1, the timer will be running because if this is 1, the clock will flow through. Any questions? Again, simply, this bit 2 is connected, this pink one. It was called the clock source. Do you remember? It is connected to what is this? Does anybody remember what is this shape?
Alo mu hocam?
No, it's not an alo. Simpler, something simpler. And this is something that selects either of these inputs according to the value of this control input. So if this control input is 0, it gets this input and allows it as the output. If this is 1, it ignores this one, it gets this one and allows this as the input. Do you remember this component from logic design? What was it called? Anybody? It's called a
MUX mu hocam?
MUX,
Multiplexer mu?
multiplexer, exactly. A multiplexer is a device which makes a clever selection. If this is the control bit, if the control bit is 0, this input is provided through as the output. If this bit is 1, this input is provided through the as the output. Do you remember, guys? In the datasheet, let's open the datasheet again. We'll remember it. I closed the datasheet. I didn't. Okay, so as you can see, the clock source. If it is 1, it was the system clock. If this is 1, as you can see, this processor clock will be provided inside. If this is 0, an external clock is provided. So you don't have to look at the datasheet. The diagram shows it all. If this is 1, the processor clock will be allowed inside. The diagram actually carries all the information. This is something embedded programs always use because it's a nice schematics of what all the system is all about. You don't have to check the bits and data sheets. It's written all over here. Okay. For example, the bit 1, the second bit from left, was the interrupt enable bit. This system creates an interrupt when it hits 0. So when it hits 0, this guy became 1, you remember? And this is the interrupt enable bit. And this is 1. I'm enabling if this is both 1, this guy will be 1. And this will be the interrupt source that I provide to the interrupt controller. So as I can see, looking at this, so to enable interrupts coming from this device, I have to make this bit 1. If I make this bit 0, no interrupts will be read. So guys, let's look at this part as well. The counter, it's decrementing. So this is a decremental counter. This is a counter circuitry. like the counter you've seen in logic design. When it is 0, is it 0? Yes. Then read the red value and copy it to here, and also set count flag to 1. All we have learned simply summarized in a schematic architecture. Any questions about the architecture? Get used to reading things like these. I mean, if you care to become an embedded programmer, guys. And some of you will, I mean, because the world is going there. Most of the electronics and computer engineers, the computer engineers, they don't like this stuff. This 2-bit hardware and low level for them. This is our job. And most of you will have to become this because most of the jobs in the world will be embedded systems. I mean, because by the time you have your grandchildren, there will be robots everywhere. That's why we will have zillions and zillions and trillions of embedded systems that had to be designed and programmed and written by many, many, many embedded programmers. So get used to this if you care to become proficient in this field. Okay, good. We got this, I guess. We got this. If you make a simple procedure of initialization, we'll be able to do it. Good. So how to initialize the system? Well, initialization depends on what you want to do with the system. Remember, because in GPIO, the first week we have written an initialization code to initialize only the LEDs. The next week, we have changed the initialization routine in which we initialize both LEDs and switches. And the other week, when we learned interrupts, we have further changed the initialization for GPIO. We have made it possible to use LEDs and switches, and we also initialized interrupts for the switches. So the initialization routine depends on what you want to do with your system. So I will provide different initialization routines. The first one will be a timer initialization, which we will not be using interrupts because we are going to make this bit 0. So to make this bit 0, we'll need to put some necessary values in some necessary registers. Okay. This is the counter, reload, and current values are undefined at reset. So at reset, when it says undefined in a system, it means you don't know the exact value of it. So you'll have to set it yourself. Just set it. I mean, there could be any random value it says. The correct initialization sequence for a SysTick counter is you first set the reload register, then you clear the current register by trying to write a value on it. You configure the register for required operation, interrupt-based or non-interrupt-based, then you enable it. So actually something written here at step 0, disable the timer maybe, and step 4, enable the timer. Because while we are doing these steps, we don't want the timer to decrement. We want the timer to be frozen. That's why when you make an initialization, first disable the timer, do your control register initializations, then enable the timer. It will be starting. Or maybe you don't want to just enable it directly, just let it frozen. In your code, at some point, it will start counting. It depends on you. Good. So how to do it? I told you, we can create actually, depending on the interrupt choice, we can create 2 types of operations. We can create interrupts with this device. We can create an interrupt with this device. In that case, we'll be writing interrupt subroutines. Or if we don't create interrupts, we won't create interrupts first, not today. We can just check the current value ourselves in the main code. And if it's a specific value, we can do something. Or remember, guys, when the current value hits 0, the control register becomes 1. We can also check this one for 0. For a specific current value, timer value, we should check the timer current register. But if you want to check if it reaches 0 or not, we could check this bit as well. That's also an operation. And checking a bit on and on and on again without an interrupt was called busy wait operation. Because while you are checking that bit, you are busy waiting for that bit, and you are not able to do anything else. Remember? That was called the busy wait. That was something that we don't want to do, but for the sake of simplicity, we are going to first just propose a system without an interrupt capability with the timer. Okay? Then we check the current value for more complex operations if we just don't want to check 0. Let's say I'm going to do something when timer becomes 1110111. Well, you can just busy wait for that value reading the current register. But remember, this is another interrupt-based operation. And if you're checking the STCURRENT register or the count flag, whatever it is, you won't be able to do anything else. That's why it's called a busy wait operation. Any questions? Good. I think you got it. I mean, it's something. It's not simple. I mean, if you have seen this system like 10 weeks ago, you would definitely not understand it. But with all you have put on top of the things that you've learned, it's something easy for you guys to understand. Okay, let's go over this busy wait operationalization. So that's the code. So at the beginning of my code, I have something like, guys, so this is a subroutine. So I have a main code, but before the main code, I have some directives. And some of the directives are like this, guys. N, V, I, S, T, control, register, equal, some value. Which value? This value, guys. Sorry, this value, guys. Plus 10. This is the value. Sorry. That's why whenever I use this word, the code will understand that it is the control register. And for reload register and current register, I have the same. What values are they? Just check the data sheets. I mean, for the reload register, it is this, it's almost the same number, but not ending with hexadecimal 10, ending with hexadecimal 14. Just you get the numbers. Okay, guys. So what happens here? What I first do is, remember, I first disable the clock so that while I'm changing the values, nothing changes. The clock is frozen. How to disable this device? I have to make this enable bit 0, right? I'm going to make this 0. I make R1 point to this address. I load 0 to R0, and I store the value inside R0, which is 0 to R1, which will try to make everything 0. You won't be able to touch these. You won't be able to touch this because it's a read-only. These will be 0. Do I want these to be 0? I don't know. But I don't care because even this is 0, it is disabled. If I need different values for these registers, for these bits, I'm going to put them later. The only purpose I'm doing these lines is to disable the timer. And when I make this bit 0, it is disabled. So I don't bother. I make all of them 0. I don't care about the other bits. This is 0. It's disabled. Any questions about this part? Good. Now I'm going to be setting a value to the reload register. So I make R1 point to the reload register. I put a value inside R0, FF, FF, FF. And if the clock is running at 16 megahertz, what will the period will be? Let's try to calculate. How many bits is this? These are all ones. How many bits? How many bits, guys?
24 mu hocam?
Exactly, 24. That's the maximum value it can get, by the way. That's the maximum value it can get. So this value is actually at R0, I have in decimals 200 to the 24 minus 1. So this is n. And remember, the period of this timer will be n plus 1 times, since this is like 62.1 nanoseconds. 62.1 nanoseconds. Well, let's try to calculate this. I'll get help from MATLAB because this is a bit complicated design, guys. 2 to the 24 times 62.5 times, it's a nanosecond. So to make a nanosecond calculation, how many seconds in a nanosecond is a nanoseconds? 10 to the minus nanoseconds 9. Thank you very much. Because milliseconds is 10 to the minus 3, microseconds is 10 to the minus 6, and as your friend says, it's 10 to the minus 9. Just I'm calculating. Ready? It's around 1 second, guys. So at each 1 second, this device is going to wrap up to 0. If you want to make it exactly 1 second, what should the value will be? What should the value will be? What should the value be? I'm sorry. You calculate it. Let me just give you as an homework. We'll solve it next week because this is something we're going to solve next week. Okay, guys, I set this reload value. And I know that it's going to create a period of something like 1 seconds. Good. Now, I will try to write a value to current register. How do I do that? Again, R1 pointing to here. I make R0 0, and I write the value inside R0 to R1. And STCURRENT register becomes all 0. If this was not 0, guys, imagine this was 10. It wouldn't have changed anything. STCURRENT would have become again 0, guys, because that's the mechanism. The value that you are trying to write doesn't matter because you are trying to write it. It is read-only. It doesn't allow you to write. It just realizes that you are trying to write. The guy is trying to write to me. I should be 0 then, it says. Good. We have cleared the time. So it's set. It is 0 now. It will start decrementing. Since it's 0, in the next clock cycle, it's going to be 0 FFF, FFF. That's it. 0 FFF, FFF. Now, guys, at this point, we have set our values, but it is disabled. I want to enable this device. To enable it, I'm going to make this one. Okay? Do I want to use interrupts? Not for this one. For this initialization, I want interrupts to be disabled. Then I make this bit 0. Which clock source I'm going to use? We'll always be using the internal clock source of this device. Then this bit should also be 1. I want the register to be 1. The other values, this is read-only, I don't care, and zeros. So I'm going to write this value here. This is binary. What is this value, guys, in hexadecimals? It is 5. That's why I'm writing 5 here. Enable, but no interrupts. Interrupts will be studied later. That's why it's 5. 5 is the code word for enable the device, but do not enable the interrupts. When this instruction is run, after this instruction, and just after this instruction, it will immediately start counting from n to 0. Okay? And not this instruction, because you have set it to R0 now. You write it R0 to R1. It is in the register now. So after you run this, it will start working. Good. Any questions? Good. Something easy. So a subroutine, guys. I'm going to go over a subroutine. We are going to go over these on live code session. Don't worry about it, but it will be easy for you. I mean, so time delay using busy wait. This is to create. What does it do? Code now do. Time to wait. Yes, this code is, sorry, I just got it. This code is checking if this flag becomes 1. Because this flag becoming 1, the control register, means that the timer has touched 0. If our system is not 80 megahertz, it's 16 megahertz, and we have initialized it with FFF value, and we have calculated that this guy will be 0 every 1.0486 seconds, so around 1 seconds. Around each 1 second is going to be 1. So we are going to check if it is 1 or not. Sorry. How I'm going to do it? So there's a subroutine for it. It creates a delay. How much delay it creates? It creates a delay with the value of R0. So in R0, if we have a value, it's going to create as big as the value in R0. Okay? So in R0, let's say there is the value 10. Okay? Let's make a test. You put the value R1, you make R1 point to reload register. This is the maximum value, guys. So 10 is equal to n. It is being, so you subtract, so R0 becomes 9 at this point. You put 9 to the reload register here, okay? And you write over the current register, you make it 0. And you make R1 point to the control register. So it's changing the initialization reload value. As you can see, this was initialization, but it is writing over it. It's doing for another purpose. I just remembered the code now. So at this point, we are R1 is pointing to the control register. Inside the loop, this is a loop, guys. This is a loop. As you can see, this jumps back with a condition. I read the value which points to R1. R1 points to this register. I read this value to R0. I end R0 with this value, guys. Zeros, as you can see, and zeros. So this is 1. I mean, this corresponds to this bit. If this is 1, the end operation will be non-zero. If this is 0, if it didn't hit 0 yet, the answer will be 0. If it is 0, BEQ, jump back. I haven't reached it yet. When I reached it, continue. So it is like wait for R0 times 62 nanoseconds amount of time. So when you call this subroutine, what it does is you put a value in R0. It waits for R0 times 62.5 nanoseconds. So it's like a delay routine. So in MATLAB, you have this. You have something like, was it pause? Pause. Yes, pause. When you say 1, it pauses for 1 second. I can write it. Pauses for 1 second. If you pause 2, it pauses for 2 seconds. So that 2 is like the R0 here. When you call this function, you put a value in R0. It waits for 1 second or less, depending on the value you put R0. So this is like a delay routine you can use. Any questions about the delay routine? Good. Good. I think that's enough. Interrupt operation I'm going to cover next week with the live code. So I think you are good to go with the timer. You can just study on your own so that you'll be prepared for it on the next week's live code.